Imagine gazing at the skyline and witnessing a dawn that fills half the sky. NASA has published images of an unprecedented occurrence where a star named Betelgeuse lost a significant portion of its outer layer, ejecting a colossal amount of its mass. This phenomenon is referred to as a surface mass ejection, SME, and according to the space agency, the expelled material was 400 billion times the mass of an ordinary solar flare from our Sun. Scientists characterize the event as observing stellar evolution in real time, with a star releasing such enormous fragments of its physical form. Surprisingly, this catastrophic explosion of the super-red giant is challenging much of what we understand about the universe. Why did Betelgeuse lose its outer layer, and what implications does this have for the cosmos? Let's explore. Constellations consist of numerous stars arranged based on mythology and legends. They continue to serve as navigational aids today. One such star is Betelgeuse, among the largest and brightest stars in our night sky. The brilliant ruby-red shimmering star known as Betelgeuse is located in the upper right shoulder of the winter constellation Orion the Hunter. When observed closely, astronomers recognize it as a volatile entity with a 400-day-long cycle of regular pulsations. Due to its distinct orange-red hue, Betelgeuse is easily identifiable. It serves as a compelling example for skeptics that stars indeed exhibit various colors. It is also known as Alpha Orionis and is the second most luminous star in the constellation, following the blue supergiant Rigel. Despite Rigel's brightness, Betelgeuse is designated Alpha Orionis due to its luminosity, size, and reddish tint, making it one of the most recognized stars. It's notable that this star inspired both the character and the film Betelgeuse. Betelgeuse ranks as the seventh brightest star visible from most of North America, Europe, and Canada, and it is the 10th brightest star overall in the sky. Earth lies relatively close to Betelgeuse. Astronomers have difficulty determining its exact distance from our planet, but they estimate it to be between 430 and 724 light-years away. Betelgeuse is the most luminous red supergiant star nearest to Earth. In our galaxy, only about 200 red supergiant stars have been identified. The Sun has a radius that is roughly 764 times smaller than Betelgeuse. If this star were to replace our Sun in the solar system, it would extend past the asteroid belt and even beyond Jupiter, indicating that Earth, Mars, Venus, and Mercury would all be entirely engulfed. Betelgeuse is 16,128 times as massive as the Sun and has 126,000 solar luminosities, making it visible from 548 light-years away. The star has a surface temperature of approximately 3,600 K, rendering it cooler than the Sun. Only about 13.3% of Betelgeuse's emitted energy is visible light. If human eyes could perceive light across all wavelengths, Betelgeuse would surpass Sirius as the brightest star in our night sky. Betelgeuse loses roughly one solar mass every 10,000 years. The red star is encircled by a nebula, as this material is being ejected unevenly from the star in all directions. A cloud of material 250 times larger than the star envelopes Betelgeuse, and the nebula's size is believed to be 30 astronomical units, or 30 times the solar distance between the Sun and Neptune, the outermost planet in the solar system. Our solar system's Sun regularly releases mass into space, known as solar flares. However, the Sun only emits tiny fragments of its outer atmosphere, referred to as the corona, hence the term coronal mass ejection, CME. Consequently, coronal mass ejections and surface mass ejections can occur separately. When a star expels a section of its unstable outer atmosphere, it results in a CME known as the corona CME. Coronal mass ejections from our solar system occur quite frequently and can impact Earth and its inhabitants. CMEs can travel more than 1,800 kilometers per second while releasing magnetic fields and plasma into space, occasionally reaching Earth within hours. A CME can disrupt and damage satellites and power systems on Earth when it originates from the side of the Sun that faces the planet, and it can sometimes endanger astronauts in orbit. The recent discovery illuminates the unique cause of Betelgeuse's event. In 2019, the material that the star expelled exploded into space, cooled, and formed a cloud of cosmic dust that obscured Betelgeuse's brightness from ground-based observers. Furthermore, Betelgeuse's well-known steady pulsing pattern has been altered. The CME on Betelgeuse is extraordinary because it released 400 billion times more mass than a typical CME, causing the star to vibrate like a dish of gelatin. According to a NASA news release, astronomer Andrea Dupree from the Center for Astrophysics stated that the star's internal convection cells may be in disarray while the photosphere, which is what we perceive as the star's surface, struggles to restore itself. Astronomers have been monitoring the star's consistent pattern for the past 200 years. Yet it no longer exists. All red giants, including Betelgeuse, are dying, and being able to observe this process will enable researchers to learn a great deal about the evolution of stars. Most stars in the universe are powered by nuclear fusion, which eventually depletes and leads a star to undergo a series of fascinating stellar transformations before it ultimately dies. When a star is born, it consists of hydrogen, which, under gravitational forces, fuses in the star's core to create helium. In a nuclear explosion, substantial heat and light energy is typically released during the fusion process. This energy travels to the star's surface and is released as a photon into space. As the star ages, its primary fuel, hydrogen, diminishes, and helium begins to fuse with carbon to form carbon. After helium is consumed, neon will eventually combine with carbon to create iron. When this occurs, the fusion of neon with iron absorbs energy instead of releasing it, leading to a collapse of the star under its own immense gravity. When iron fusion begins, the star implodes, resulting in a supernova explosion. A supernova, one of nature's most powerful forces, can generate more energy than 10 billion suns. Stars change color throughout their existence, from the youngest, hottest blue types to the older, cooler red varieties, depending on their stage of stellar evolution. The Greek scientist Tyson in 168 AD oddly referred to Betelgeuse's hue as having a ruddy tint. 3 centuries earlier, Chinese astronomers described the star as appearing yellow, possibly suggesting that Betelgeuse was formerly a yellow supergiant. Astronomers may gain insights into how red stars lose mass in their final days before exploding in a brilliant supernova from Betelgeuse's explosion. As one astronomer remarked, "We've never observed a massive mass ejection on the surface of a star before. We're left with something happening that we don't completely understand. It's a completely new phenomenon that we can observe directly and resolve surface details with Hubble. We're witnessing stellar evolution in real time." Nonetheless, it remains unclear whether this occurrence signifies Betelgeuse's imminent supernova detonation, given the peculiarity of the findings. NASA cautions that Betelgeuse may not have reached its life's conclusion, even if it appears to be approaching it. Cosmic timespans are vast, and red supergiants tend to perish quickly in comparison. According to NASA, Betelgeuse is predicted to explode within the next 100,000 years. Betelgeuse has been extensively studied since the 1st century BCE. More recently, a researcher named Sarah Nance and her team aimed to determine the likely timing of supernova explosions in red supergiants like Betelgeuse to understand how such a massive star would behave over time. Nance and her team carried out numerous simulations using Betelgeuse as a model and then compared their results with observational data. Why did Betelgeuse suddenly diminish and fall out of its typical cycle when it is not expected to detonate for another 100,000 years? Betelgeuse was expelled from its origin in the Orion OB1 association, which includes the stars of Orion's belt, and has been noted moving through the interstellar medium at a speed exceeding 1 light-year per year. By mid-February 2020, Betelgeuse had lost approximately threefold in brightness, from magnitude 0.5 to magnitude 1.7, after beginning to decline sharply in October 2019. By February 17, 2020, Betelgeuse's brightness had stabilized for nearly 10 days, and the star began to brighten once more. However, Betelgeuse seemed to have entirely ceased dimming 5 days later, effectively concluding the dimming episode. Given the lack of significant changes in the infrared on February 24, 2020, it appeared that the recent visual fading was not linked to the anticipated core collapse. Another investigation concluded that the star's dimming was most likely due to a cloud of large-grain circumstellar dust. Dust absorption was ruled out as having a significant effect in a study utilizing measurements at submillimeter wavelengths, but the fading seems to be caused by large star spots. Further examination indicated a significant increase in Betelgeuse's brightness between May and August. Betelgeuse is so near to the Sun that it is nearly impossible to observe from Earth. Before 2020, when Betelgeuse was in conjunction with the Sun, it was visible at a magnitude of 0.4 for brightness. Observations made with the Stereo A satellite in June and July of 2020 showed that the star had dimmed by 0.5 since its previous ground-based observation in April. This surprised everyone, as the maximum and subsequent minimum were expected in August and September 2020 and around April 2021, respectively. Betelgeuse's brightness was known to fluctuate widely, complicating predictions. The fading suggests that a second dimming event may occur much sooner than anticipated. The identification of a second dust cloud associated with Betelgeuse in June 2020 suggested that a cool patch on its photosphere might be responsible for the dust. In August, a second independent study confirmed the initial hypothesis. The dust is thought to have formed from the gas expelled by the star. Research conducted in 2022 using the Hubble Space Telescope indicates that a dust cloud may have originated from a surface mass ejection. The material released from the star's surface, millions of kilometers away, cooled, condensed, and formed the star's obscuring dust. The fragmented photosphere, which was several times more massive than our moon, was expelled into space, cooled, and created a dust cloud that obscured the star from the view of observers on Earth. The fading, which began in late 2019 and persisted for several months, was clearly noticeable even to amateur astronomers tracking the star's brightness changes. Even more astonishing, the 400-day pulsation cycle of the supergiant has vanished. For around 200 years, astronomers have monitored this cycle by analyzing changes in Betelgeuse's surface motions and brightness variations. Its disruption reveals the magnitude of the event. Astronomers have developed a potential theory to explain the anomaly. The star is also gradually rebuilding strength, and the photosphere is regenerating. The star's normal cycle is being disturbed, and the interior is vibrating like a belt that has been struck. A massive stellar surface mass ejection has never been recorded before. There is still much that we do not fully understand. We may directly observe this new phenomenon and use Hubble to discern surface features in real time. When will it happen? Probably not within our lifetimes, but in truth, no one knows. It could be tomorrow or a million years from now. Will Earth be destroyed by Betelgeuse's supernova? No. The explosion of Betelgeuse will not impact or partially extinguish life on Earth because it will occur too far from our planet. Astronomers estimate that for a supernova to pose a threat to humans, we would need to be within 50 light-years of it. Betelgeuse is more than 10 times that distance. Instead, everyone on Earth will be treated to an extraordinarily spectacular view of a very bright star in the night sky. Ultimately, due to Betelgeuse's proximity, astronomers will be able to study the star when it undergoes a supernova. Betelgeuse is currently not visible in the night sky, so don't bother searching for it. Even if it went supernova right now, we wouldn't notice it much unless it were in the midday sky during August. Betelgeuse might have already exploded 5 to 29 years ago, and we have yet to see its light. Scientists are thrilled about the prospect of witnessing Betelgeuse's monumental eruption and recovery. In the meantime, NASA's James Webb Space Telescope may be able to track the expelled material from Betelgeuse as it travels through space, while the Hubble telescope continues to investigate the star. In addition to the fascinating phenomena surrounding Betelgeuse, its significance in enhancing our understanding of stellar physics is crucial. The immense scale of Betelgeuse's surface mass ejection challenges existing models of stellar behavior and evolution. Traditionally, the mass loss process in red supergiants has been understood through steady, predictable mechanisms. However, Betelgeuse's recent explosive event reveals a more chaotic and violent side of these stellar giants. One aspect of Betelgeuse's behavior that has intrigued astronomers is the potential for such events to serve as precursors to supernovae. The irregularity and scale of its mass ejection might offer insights into the final stages of a star's life cycle and the nature of supernova triggers. By studying Betelgeuse, scientists hope to identify the factors that lead to such dramatic stellar transformations and refine predictions about supernova occurrences in similar stars. Furthermore, Betelgeuse's situation highlights the complex interaction between a star's internal processes and its observable phenomena. The interplay between the star's core dynamics and its outer layers during these massive ejections may shed light on how other supergiants evolve and eventually explode. This understanding could have broader implications for the study of galaxies and the distribution of elements across the universe. Betelgeuse's recent behavior also underscores the necessity of multi-wavelength observations. While optical telescopes provide valuable information, the use of infrared and ultraviolet observations is essential for capturing the complete extent of the ejected material and its impact. Instruments like the James Webb Space Telescope and various ground-based observatories play a vital role in assembling the comprehensive picture of such stellar events.